Hey folks, in this video we will be talking about a velocity that is both changing direction and speed. We'll look kind of mostly conceptually at it at this point, and we'll hit this in a lot more detail when we hit rotational motion second semester. But I know students often have questions about this, and so I want to make sure that they are answered now, and so you're not left in some sort of mystery. So let's look at the first example here, which is an object that is getting faster and turning in the clockwise direction. So something like, well, actually, hold on. Let me make this motion map a bit better. It starts off with a slow speed in that direction, and then gets faster. We'll label these 0, 1, 2, 3. And so maybe something like that, where it's moving and the distance it covers each second is increasing. We'll put arrows to represent that clockwise direction. All right. The net force we know must have a radial component to it, so we'll call this one F1, maybe a smaller force F2, but there will always be an F1, or the net force for this object will always point toward the center of the circle. Looks like I need to move that 2 out of the way. There we go. All right, so we're always going to have a net force toward the center of the circle. So the sum of the forces in the radial direction is equal to F1 minus F2, and that's equal to m times your centripetal, or so your radial acceleration in the radial direction. So this is acceleration needed to turn. However, these forces will not make the object get faster or slower. And so we're also going to need something in the direction we are moving. So we're also going to have a force F3 in that tangential direction that is always in the same direction as the velocity. So if we add up the forces in the tangential direction, we end up with just force 3 as I've drawn it, and that's going to be equal to mass times your tangential component of the acceleration. And this tangential component is the acceleration needed to get faster. And this is the tangential acceleration. This one is the one that you can use your kinematics equations with. So we can use things like your tangential velocity is equal to your initial tangential velocity plus your acceleration in the tangential direction times time. We can use the distance you cover. X and Y probably isn't great as we go along the circular path. So I'll use just distance, I guess. I'll just write it out. Distance here is going to be something like, let's see, your initial velocity in the tangential component times time plus 1/2 times your tangential acceleration times time squared. All of these equations that you know and love work for the tangential component of the distance covered. Here, if you're talking about a radial, so I'm going to highlight all those in yellow, all of those work. If you're talking about the radial component of the acceleration, then none of those equations work. And instead, you've got to deal with the fact that your radial component of the acceleration is your speed squared over your radius. That is the one equation that applies for the radial component of the acceleration. So we have two pieces of acceleration to consider. How much of it is getting me faster or slower, and how much of it is turning me. In this unit, we will almost exclusively focus on the radial component. We'll look at things that are turning at a constant speed so that we can separate them out. And then later on, we will talk a lot more in detail about the component of the acceleration making us get faster. But as an example, as a few more examples to tie in this idea, we're getting slower in turning in the clockwise direction. That means we might cover a big distance, and then a little bit less distance, and then a little bit less distance. And we'll label these 0, 1, 2, 3. Again, we must have a net force in the radial direction in order to turn. And I'd like to emphasize that it must be the net force, not necessarily any one forces. So I'm going to draw a few in there. Make sure your F1 arrows are bigger than all of your F2 arrows. I also want to draw in the direction arrows on my circle. All right. So for turning, we can add up the forces in the radial direction, which would be F1 minus F2 in this example, and that's got to be equal to m times your turning acceleration. For slowing down, we're going to sum up the forces in the tangential direction, which is tangent to the circle. And if we're moving clockwise but slowing down, that means the net force must actually be in the other direction. So here, the net force must oppose the velocity, which is the opposite of what it was in the previous example. F3 equals your m times your tangential component of the acceleration. Tangent to the circle and opposite the direction of the velocity. I think those two examples actually should hit the main points. It kind of just mirror images if you're talking about the counterclockwise direction. So let's just, rather than do two more examples, let's summarize. So I had two more examples set. I think it'd be better just to delete those. Where is my delete button? Home, insert, draw. I don't know where my delete button is. All right, so we'll just scroll down then. All right. So general principles is net force in radial direction turns. But does not change how fast. And then net force in tangential direction changes how fast, but not direction of motion. And then you can have both of them happening at the same time. And then this tangential force is if it's in the same direction as velocity. That means you'll be getting faster. This is nothing new. And then if your net tangential acceleration is in the opposite direction as velocity, then you'll be getting slower. So it's just an application of what we've already learned, but now we're turning. All right, and that should do it. I hope that helps. I guess one more point I want to make. Let's look at this third example here of getting faster, turning in a clockwise direction. So now we're going counterclockwise. I said clockwise, but I meant counterclockwise. And here, we could make this happen, getting faster in this direction, with just one force. And that's the point I want to make here. So long as, and I'm going to draw in the radial direction and the tangential direction so that we can see it clearly. If we have one force that has components in each direction, we'll call this F naught. I don't know why. It has a radial component to it, and it has a tangential component to it. And so F naught both increases speed with its tangential component, and turns with its radial component. So you don't necessarily need two forces to make this happen. You could also have one force that has components in both the radial direction along the radius and the tangential direction tangent to the circle. All right, so that should do it. I hope that gives you a nice sort of big picture overview. Like I said, in the future we'll probably focus mostly on things turning at a constant speed where there is no net force in the tangential direction. Actually, I want to really emphasize that point because that's where a lot of students get confused. So if constant speed, then net force in tangential direction is 0. Oh, that's not how you spell 0. And you know it's important because it's in all caps the same way that a lot of dads write. And so there we go. I'm going to grab a highlighter here, doubly, triply highlight it. All right. So with that, I hope that helps. We'll look at more concrete examples later on.